Hello, thanks for watching, and welcome to the next video in my series on basic statistics. Now, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit up to this point. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist, because that does encourage me to keep making them. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. Therefore, I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. So all that being said, let's go ahead and get started. This video is the next in our series on inferential statistics. So in the previous video, we looked at point estimation, and that's where we are using an empirical measurement from a sample to make some statement or inference about a larger population from which it was taken. Because remember, in a large population, say everyone in England or all the products coming off an assembly line, we cannot measure characteristics for every single one of them. The time and the cost and the hassle would just be tremendous. So we take samples, and then we develop statistics based off those samples that are then supposed to be somewhat representative of the overall population. But of course, they're not perfect. So in this video, we're going to talk about the properties of those samples, and we call these sampling distributions. So we can take samples, several samples from larger populations, and then we can make some conclusions about that larger population based on the samples. So let's go ahead and get started. So let's run through this example really quickly because it's the same one we used in the point estimation, so I won't go into a whole lot of extra explanation. But we have a company called Highway Paving that is they specialize in residential road surfacing, so road surfacing in neighborhoods. Many of its clients seek out its specialized product, low noise pavement. So recycled rubber can be added to asphalt mixtures to reduce road noise, which appeals to environmentally conscious clients. So the rubber from like old tires is ground up and reused in asphalt. And so that saves them from going into landfills. And then, of course, the road noise from the tires rolling across the pavement is reduced, which is good inside and outside the car. So it's a win-win. However, the viscosity, that's sort of the resistance to flow. Remember, viscosity is about how a substance flows, whether or not it flows readily or it flows very, 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 very slow. So the viscosity of the asphalt has to be maintained within a very tight limit. Otherwise, it may be too thick to even you transport or spread out on the road, or it may be too sort of watery and it runs everywhere. So it has to be just right in terms of its viscosity. Now the goal for this product is a viscosity of 3,200. So during the manufacture of each batch of asphalt, the quality control specialist in the company takes 15 specimens or 15 measurements. I should have changed that word sample there. So I use that word differently, which we'll talk about here in a minute. It takes 15 specimens of the material and tests its viscosity back in the lab. This also ensures that the batch has uniform viscosity. So we want to make sure that the viscosity meets our target, and in this larger batch, that the viscosity is uniform. There's no clumps sort of in one area that are thicker, and there are no spots in the batch that are sort of more watery or, or thinner than the rest. So we want to make sure that the viscosity is uniform. So some points of note. There's no way to test every single ounce of asphalt. Now think of the overall batch of asphalt as our population. Therefore, the company has to take samples. Now from those samples, the company must then make inferences about the entire batch. So it takes the specimens back to the lab, measures several of them, and then based on those results can say, yes, our batch meets our standards and it's uniform or not. Now, the inferences made using samples are by definition incomplete. And that's sort of the idea of inferential statistics. We are making some claim or some conclusion or an estimate about the population based on a smaller subset of that data. So it's never going to be perfect. It's always going to be incomplete. Therefore, the sample characteristics will always have some error built in. So here's the first sample. So they take 15 specimens from the batch, and we have viscosity figures of 3193 for the first specimen, 3124 for the second, etc. So the mean of the sample is 3,210.73, and the standard deviation turned out to be 117.61. So these are 15 measurements, or 15 specimens, that make up the first sample. The first sample. So this first sample has its own distribution. So it looks like this. And again, that's sort of the normal curve that we are familiar with. And it has the mean of 3210.73, standard deviation of 117.61. And there we can put x sub 1 is 3210.73. Now the subscript 1 there means that that is our sample mean for the first sample. So x bar sub 1 means the sample mean of our first sample. Now remember, the company's goal is a viscosity of 3200. Our sample mean was 3210.73. Now since this is the sample mean, we don't expect it to be exactly 3200. But is 3210.73 close enough to our goal to be acceptable? And the question is, does this sample accurately reflect the viscosity parameter of the overall batch or the population? Just to review, we use the term parameter to talk about the characteristic of a population. So the population mean is a parameter. The population standard deviation is a parameter. The sample mean is a statistic. The sample standard deviation is a statistic. So parameter versus statistic. Now the answer, I know, is yes, but the question is, how can we statistically determine that? Now, one way we can do this is to take multiple samples from our population. So up to this point, we've only taken one sample, and that one sample had 15 specimens in it. But we could repeat that process multiple times, and that would tell us a bit more about our population. So let's say we go ahead and do that, and we take 9 samples, each of size 15. So 9 different samples of our population, and each sample has 15 measurements in it. So we just repeat what we did 8 more times. And this is what we come up with. So our first sample had a sample mean of 3210.73, which we already talked about. Our second sample had a mean of 3150.13, and so on and so forth. So each sample is comprised of 15 separate measurements. So we just do the sampling process multiple times. And it looks like this. So we have our 9 samples. So you can see x bar sub 1, x bar sub 2, x bar sub 3, etc. And each one has its own mean and deviation. So it might look like this as far as a collection of sample means. Now, the question is, what is the distribution of these sample means? Now, one way to do that is to think about it as a histogram or a count, right? Let's look at this. Now, what I've done is I've created count ranges for our means. So you can see the first range is 2950 all the way up to 3049. Technically, it's 3049.99. 3050 to 3149, 3150 to 3249, etc. And then what I've done is I have put tick marks, I've counted how many of our sample means are in that range. So we have one sample mean that is in the range of 2950 to 3049, and let's see, that is down at the very bottom. That's sample number 9. So sample number 9 is in that range. And then there is one sample mean that's in the range of 3050 to 3149. Then there are 4 in the next range, 2 and then 1. So we've created a histogram of the sample means themselves. Now we call that the sampling distribution. It is the distribution of several sample means. In this case, 9, but we could have done 20 or 30. But it's a distribution of the sample means themselves. Now when we do that, we come up with a histogram that looks like this. So again, we have each range at the bottom and then the counts on the left-hand axis, the vertical axis. So we can see 1, 1, 4, 2, and 1. Now, does anything about this general shape look familiar? What if I were to take the normal bell curve and put it on top of this distribution? Aha! See what we're getting at here? Now, the sampling distribution is going to have its own sort of shape, and hopefully it comes out to be sort of a normal distribution shape. But again, we're getting a bit ahead of ourselves, but you can see where this sampling distribution comes from. It's actually a distribution of the sample means themselves. So the expected value, or the mean, of the sampling distributions. So here is our chart from our previous slide. Now the expected value of our sampling mean, our sample distribution mean, is equal to the population mean. So if you look over here on the right, that's what we're going off of. So the expected value of X bar, which is our sampling distribution, should be equal to the population mean. So you can see what we're looking at here is E X bar is the expected value or the mean of this sampling distribution over here on the right. Okay? So the sampling distribution mean is equal to the population mean, which we do not know. And that's the idea behind the sampling distribution. Now I'm going to break this little bit of text down very slowly. It's plain English, but it's kind of riddle-like. So let's take it one bit at a time. If we take many random samples from the population, each one of those samples will have its own sample mean, okay? Which is what we just did. Those are the 9 sample means we had. Then we create a distribution based on those sample means. So we take many samples, then we create a distribution based on those sample means. Then when we do that, the mean of that sampling distribution is equal to the mean of the population. Okay? So we take many samples, each with their own sample mean. Then we take those sample means, we create a distribution like this one here on the right, and then the mean of that sampling distribution is equal to the mean of the population. Okay? And that's the idea of a sampling distribution. Now, of course, it's an estimate at best. The expected value of the sampling distribution of X bar is at best going to be an estimate of mu, which is the population mean. We would have to take every conceivable sample from the population to match the population mean perfectly. But if we do that, what's the point of sampling in the first place, right? So we do sampling to get around having to do that. The best we are going to be able to do is to find an interval estimate for the population mean mu. So again, when we see on TV, when they do a presidential poll, it says 53% of likely voters say they're going to vote for this person. And down below, it says margin of error plus or minus 3%. Well, that's because they took a sample of likely voters. They didn't ask every single one of them. They took a sample. And that's going to have some error built in because it's not going to be completely perfectly representative of all likely voters. So we find an interval estimate for that population mean. Our interval estimate will be influenced by sample size, and this should make sense. So again, in the presidential example, what do you think's better? If I go out and ask 4 people who they're going to vote for, or I go out and ask 1,000? Well, I would say that asking 1,000 is going to be more representative of the entire population than asking 4. Okay? So it is influenced by sample size and the degree of confidence we are satisfied with. So if we want to be very, very confident, then the sort of range of errors are going to be different than if we're willing to be a little bit less confident. And we'll talk about that in future videos. Okay, so that wraps up our video on sampling distributions. And this is a very, very important concept that a lot of students don't really understand. That when they see in their text, oh, the sampling distribution, well, what is that? Well, the sampling distribution is a distribution that is based on sample means themselves. So the samples produce sample means, then we do a bunch of samples that produce a bunch of sample means, and then we take those sample means and we put them into their own distribution. And the mean of that distribution is the population mean. Okay? So, again, this is just one of those fundamental ideas to get under your belt before you go into more sort of advanced areas of statistics. Okay, so just remember, if you're watching this video because you are struggling in a class, I want you to stay positive and keep your head up. You're smart and you're talented, and you may just hit a temporary rough patch. So I have faith in you, and so does everyone else around you. So should you. Feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you know about it. Please, if you like it, give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. If you think there is something I can do better, leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones. And finally, just keep in mind that the fact that you're on here trying to improve yourself as a student or as a business person or just learning more about these topics, that is what's really important. If you have the right learning process in place, the results will take care of themselves. So, thank you very much for watching. I wish you the best of luck in your studies and in your work, and I look forward to seeing you again next time.